Let's talk about line integrals, which really should be called curve integrals. In fact, they are in some languages, but not this, because it's the area under a curve. So what we want to do is find the area under some curve that's in 3 dimensions. In this case, it's over the xy plane, but it doesn't have to be, or it's projected down. So maybe you want the area, maybe you want you're painting a fence, and you want the area underneath it. That's probably the worst application I could possibly think of. Could be the density. You look at the density everywhere, and then the density is higher here than it is here, and it just gets smaller and smaller as you go. And so the integral of the density function is going to give you the total mass, and then you can find center mass and things like that from there. So the way they do this is your line integral here, is it's this as well, is what's happening here is a function is going to be defined on the line. So as you go along the curve in space, there's a function associated to it. So it could be the temperature everywhere. All right. The function's defined on it. So it could be the temperature as you go. It could be the density, like I said. So these lines are normally given as a parametric set like this, or as R of t, a vector set. R of t is x of t, y of t. Now, with that said, we're going to convert this here to this instead. So what does this mean? ds is just a little piece of the arc length across. So this corresponds to dx or dy in Cal 1. So, but in this case, instead of like a little piece delta x, see, if you remember in Cal 1 what you did, let me just pull some over here. In Cal 1 what you did was you have a curve, and then you want to find the area under the curve, and you split up the axis into a bunch of subintervals here, right? And each of which had a delta x width, and then the function you were looking at, which was defined, was the height, which is the function itself, right? You added up all these rectangles. So now what's happening is the bottom piece here is no longer just the x-axis, it's a curve. It's this thing right here. It's a curve. And so the function's defined on a curve. The curve is parameterized using x of t and y of t, and so things have got to be done a little differently. The ds part is just the length along a little piece of the curve. And so the way this integral works is you're approximating the value of f in each little interval. You're multiplying it times the length in that interval. So let me pick one out. So you have something like this. You have a little interval here, and f, say f is in green. So f is going to be a sample point. Like you had a sample point here in your Cal 1 class. It could be the midpoint or the left point or the right point. It's like that. So that sample point multiplied times just a little piece in the area formula, the arc length, and you get what we have here. The ds is this here. It kind of looks like the Pythagorean theorem, and it is. If you consider that your little arc, your little piece of curve here, if you try to make it, if you're trying to find the length of it, basically it can be approximated using a tangent line. That tangent line is the hypotenuse of a triangle, okay? And so you have change in x and change in y, and you have change in s here, the change in the arc length, right? And so that's why when you square these and add, the change in x, when you take delta x going down to delta t going to 0, will be dx dt. and then change in y will be the dy dt, and that's why you have this. So it's the Pythagorean theorem, a squared plus b squared is c squared. All right. Okay, so this is how the line integral is obtained. And so let's try an example of this. So let me pause the video and pull out an example. Okay, I picked up two of them. This one is the one I want to do first. So let's bring that up. So it's integral x e to the y ds over c, and it's the line segment from 2, 0 to 5, 4. So it's this line segment from 2, 0, this is 2, and then maybe 5 is over here, and maybe 4 is way up here. So this is 4 to 5, 4, 2, 0 to 5, 4. So it's this line right here, and it's going in this direction. So we're going to parameterize it. So the line is r of t. I like to use this formula here. R of t is r naught plus tv. There's another one, but this is easy as well. So v will be the vector that's parallel to it. So this will be 5 minus 2, which is 3. I'm looking at these points. 5 minus 2, which is 3, and then 4. And then the r naught will be just one of the points. And so r of t is r naught, so it's 2, 0 plus t times 3 comma 4. And so we get r of t to be 2 plus 3t and then 4t like this. So this the first ones are x of t and the second ones are y of t. All right, so now I can just plug those in for x and y here. Okay, ds, that piece there, is going to be that square root of dx dt dy dt stuff. So the square root of dx dt is 3, so it's 3 squared, plus dy dt is 4, so that's 4 squared. So this turns out to be 5. So what we get from this integral is integral x is 2 plus 3t, y is 4t, and then times 5 dt, like that. Alrighty, so I'm not going to solve this, but what you could do when you finish it, it's 2 integral e to the 4t, which is pretty simple, dt, plus it looks like 3 integral t e to the 4t dt. This one here is by parts, looks like. All right, now whenever you use this formula here, t always goes from 0 to 1. So it would be the integral from 0 to 1 there. All right, and then you finish it out. What's going on here is the following. There's some function, x e to the y, that acts on this line. All right, it's some function that acts on that line. So we're adding up that function as it goes along that line. It's defined on it. Okay, so what I wanted to do also is I wanted to look at 5, because 5 is interesting. There's another way you can parameterize things. So let me rewrite it. It's x squared y plus sine x. All right, integral x squared y plus sine x, and then it's just dy, and it's over c, and c is the arc of the parabola y equals x squared from, let's say a is 0, 0 to b is pi, and then pi squared. Yeah, that would have to be pi squared. Pi and then pi squared. Now you can make r of t here as x is t and then y it's t squared if you want, and it's very simple. You just work it out like this. But you could also do r of x. See, y is in terms of x, so there's really no need, if you don't want to pull in t here. You could just make this x comma x squared and just parameterize using x instead. And then the dy piece, dy dx, is 2x. So the dy piece will be 2x dx. So what we get is this integral becomes integral, good old x squared stays the same. Y is x squared plus sine of x. And then the dy part is, so it's all this, and then it's 2x dx. And then it goes from, t is going from 0 to pi, or x is going from 0 to pi, so 0 to pi. So then you solve this, just looks like a Cal 1 problem, 0 to pi, x squared, x cubed, x to the fifth. That's x squared, and then 2x. I'm going to pull the 2x out, so x to the fifth plus sine of x, x sine of x. So let's put this into two integrals. This is dx plus 2 integral 0 to pi of x sine of x dx. This is easy. This is parts. Just do it by parts. All right, and so that's that one. So now I want to go on to something else. The answer to this I'm not going to do. It's just, you just finish it up. All right. So let's try something else here. Oh, that's a good one. What I want to talk about, I'll let you read this in the book. It's just an application of it, that's all. And where m, the mass, is the density times this ds. So your function now is an actual application. This is an application this time. All right. All right. This here is unusual. This is another way to write your f of x y ds. Don't get too hung up on it. Just know that this is coming up in 16.4. We're going to have a really cool application of this. So it's just another kind of line integral, that's all. It's just another way to look at it. Oh yeah, this is the parameterization that you can use for lines. So if it starts at, we could have done that 0, 0, comma, pi, pi squared. Well, no, that was a parabola. But that 2, 0 to, I think it was 5, 4. We could have used this here instead. But that's okay. All right, and so the book gives a nice example where you have to do two different things, two different integrals. And the hard part is that you have to do two, but the easy part later is that we're going to see if the curve has certain features to it. It's going to be much easier, so we'll see that in the next section too. This here in the book, just go over that. It's not hard. It's just dealing with negatives. Basically, it's this. If well, no, actually, let me go over it. If you have your curve C, the direction of C matters a lot. All right, so if you go the other direction instead, so you're going this direction instead, then instead of the integral over C of f of xy ds, or whatever, it's going to be negative integral over C of f of xy ds. It's going to go in the negative direction. We call that direction negative C, if you will. So this direction here will be negative C. All right, line integrals in space, very similar stuff. All right, you just added a dimension to it. And then you can write that dx, dy, and then now dc, you have this piece here instead. All right, it's not that bad. Line integrals of vector fields. Okay, so this is something different. So what's going on here is the following. You have some let's say force field going through. All right, and it's getting bigger and bigger, or maybe it's sideways sometimes, or whatever. Let's just say it goes the same direction. And you have a particle going through the force field. All right, whenever the force field is perpendicular to the particle, what we're going to look at is the work done by the force field F. So that's the part in green. by f on the curve, on the particle going along on the particle. It's not a particle, maybe it's an object going along the path. C. All right, so we'll call this thing C. This is C. So there's some particle going along. All right, minding its own business, and it's going through this force field. So maybe the force field is the wind, and maybe the particle is really just maybe it's a plane or something. So what we do is we're to find the work. So work is force times distance. It's the dot product. It's the dot product of these. Okay. So with that said, the distance traveled. So what you do is you split this up. And so you look at the distance traveled in a little piece, and we're going to call that dr. And then if you look, the work is the dot product of the two. So you have your force vector F. Remember, the dot product is it's associated to cosine. So it's the length of F times the length of D times the cosine of the angle between them. So if the force vector is going in the same direction as the curve, then the work done is positive. In other words, the wind has a positive, what can I say, aspect on a positive influence on the particle going along the curve. So this is a little particle going along the curve. If the force field is going perpendicular to it, like here, so you have it perpendicular, then the 90 degrees is the angle between them, and the cosine of 90 is equal to 0. So what it's saying is that there's no work done at all. The plane is not influenced at this little point right here. The plane is not influenced at all by the wind. It's just going in its own direction. It's going this way. Now, if you look at the next one over, this one here, this scenario, the angle between the two, theta, the angle between the two is greater than 90 degrees. So the cosine of angle of that will be, then the cosine here, this piece, will be less than 0. And so remember, because cosine, if it's greater than 90, cosine in this quadrant is negative. Okay, so if you want to find the total work done going along that curve, then what we're going to use instead of the distance vector, isn't that a tangent vector? So we're going to use t for our tangent vector. And so you're going to total work will be the addition of all of these dot products. I think I want ds. That's dt. Yes, ds. So yeah, obviously, because we're looking at the arc length along it. Yes, so this is ds. Now the tangent vector is, remember the tangent vector is r prime over the length of r prime. And then ds, we looked at this before, is the ds piece there is r prime, the length of r prime. That's ds dt, all right? So that's the change in s is the length of the vector, the little tangent vector. Remember, r is the curve itself. So this is, the c is given by r. So this little curve is r of t. And so r prime of t is a tangent vector to it. So if you look at the length of the tangent vector, that will give us our dt piece, or ds piece. So if we go back to this integral, it's f, and we're going to parameterize it. So we do f of x of t, y of t, like that. And now we're going to dot that with t, which is r prime of t, divided by the length of r prime of t. And then the length here. And then the ds piece is just this length, r prime of t dt. Sorry, everything's running into each other. I don't need all this anymore. All right, so then these two cancel. This here is just r of t. So we get the integral of f of r of t dotted with r prime of t dt. If you want to get a more, if you're not understanding it, the book does this as well. All right, so what this is the work done by, this is one application. It's the work done by a force field on a particle going along a path C, where C is parameterized by r of t. So C could be a circle, right? C could be a circle, and then r of t would be, if it's, let's say it's a circle of radius 2. That would be 2 cosine t, 2 sine t, like that. All right, so let's do an example of this. Okay, so we're going to look at this one. F of x is this vector field. I prefer to write it as xy squared, comma, negative x squared. And then r of t is t cubed, comma, t squared. This one here isn't real interesting. It's just this curve like this. It's kind of look like that. But the vector field is actually very interesting. So what I want to do is I want to look at a website that Kevin Mehal has done, and it's called Equation Explorer. So just Google Equation Explorer with Kevin Mehal, and you'll see the you'll see that it's really cool. So let me pull over. What I've done is I've graphed what's going on with this thing, with this problem. So here it is. You have your, let me do the little business here. So you have your curve, which is in orange here. So your things are going along fine. Your little particles going along the curve. And then you have your vector field in red. And so you're looking at the work done by the vector field on the curve, on the particle going along the curve. And so it looks like it's going to be positive over here. But if you look, I've needed to do T max to be between 0 and 10, but in the book it was between 0 and 1, and it just showed this little piece there which wasn't very interesting. What I could do is T 0 to 10, and I'm pretty sure our answer will be negative, because the vector fields, well, no, it's going to be positive, actually. No, positive. What am I thinking? Yeah, it's going in this, the particle is going in the same direction as the vectors. So it's going to be positive. If you look here, it looks like they're going perpendicular. So anyway, so let me get out of this and let's actually do the problem itself. All right, so let me take this away. Let's do this problem. So here we go. So we go integral f, I want you to memorize this, by the way, f of r of t dotted with r prime of t dt. So f of r of t, you just plug r in. So it's going to be t cubed, I'm plugging in t cubed for x and t squared for y. So it's t cubed, t to the fourth, because that's y squared. And then, so that's this, comma, and then negative x squared will be negative t cubed. No, t to the sixth. T to the sixth, like that. Yeah, because you plug in t cubed into x squared, you get t to the sixth. Yeah, and then now you dot it with r prime. So r prime is going to be 3, so r prime is 3t squared, and then 2t, like this, dt. And supposedly we're going from 0 to 1, but let's go to 10, see what happens here. All right, so this is integral of, let's go ahead and do this out. This is, this piece here is just t to the 7th. You dot it with the other one, that'll be 3t to the 9th. make this a little smaller. And then that's plus, so it's a negative here. So it's minus, let's see, that would be 2t to the 7th. We're dotting this. Prime. Yeah, and then it's dt. We go from 0. We'll do 0 to 1 first, and then we'll see what happens with 10. So now this is a 3 over 10 t to the 10th minus 2 over 8, which is 1/4, t to the 8th. 0 to 1. So this is going to be 3/10 minus 1/4, which it looks like 20 goes into both of them. They both go into 20. So this is 6 minus 5. So this is 1/20th. 1/20th, which makes sense because there wasn't much going on. The force wasn't very big there. Let me pull it back over. See, the force wasn't very big there. So there's not a whole lot going on there as far as work goes. So now let's do it from 0 to 10. Maybe not 10. It's pretty big there. I'm gonna have to do 10 to the 10th. How about 0 to 3? Ooh, that's gotta be huge. 3/10 t to the 10th minus 1/4 t to the 8th equals. All right, so I get 16,074.45. So much bigger. So sure enough, it's positive like we thought it would be. All right. Okay, let's try another one. Well, I'll tell you what, I think that's good. That doesn't get much more complicated than that. Oh, yeah, I guess we just did this one here. Find the work done with a force field and problems around the circle or in a counterclockwise direction. So you're going to have to parameterize your circle using R of t is cosine t. It's 2 cosine t, 2 sine t. 2 cosine t, 2 sine t. Like that. And use a computer algebra system to graph the force field in the circle. So that's where you can use the Kevin Mihal thing that we just did. All right.